Imagine trying to spot a single candle burning in the light of a million suns. That's essentially what astronomers are up against when they try to find Earth-like planets orbiting distant stars. Now, here's a wild idea. What if quantum physics, the realm of particles that defy common sense, could help us solve this cosmic puzzle? I mean, quantum mechanics and relativity have been at odds for decades, but this new research suggests they might just be the key to unlocking one of the biggest mysteries in astronomy, finding another Earth. Let me break this down for you. The problem isn't just the distance. It's the sheer brightness difference. Exoplanets are so faint compared to their stars that even the best telescopes struggle to separate their light. Think of it like trying to see a speck of dust next to a floodlight. But here's where it gets fascinating. The Rayleigh limit, this invisible boundary that says two objects can't be resolved if they're too close, is the real enemy. And yet, this paper from South Korea proposes a way to hack that limit using quantum mechanics. How? By treating photons not just as particles of light, but as carriers of hidden information. Personally, I think this is where the rubber meets the road. You see, photons don't just have energy, they have wave shapes, and by measuring those shapes, you can extract details that traditional cameras miss. It's like upgrading from a black and white photo to a 4K Ultra HD version. The team built an algorithm that continuously adjusts itself, using something called the symmetric logarithmic derivative to tweak how photons are sorted. But here's the kicker. They replaced human guesses about how many planets to look for with a statistical tool called the Bayesian information criterion. That's not just smart, it's a glimpse into the future of AI-driven astronomy. Let's talk numbers. In simulations, their system correctly identified 3 objects, a star and 2 planets, 72.5% of the time. One planet was 100 million times dimmer than the star, mind-blowing. And when they introduced artificial noise, the success rate only dropped slightly. But here's what I find mind-boggling. This is all theoretical. The real-world hardware isn't here yet. Yet, the implications are staggering. If this works, we could detect planets that are currently invisible to us. What does that mean for the search for life? It means we might be looking at a whole new chapter in astrobiology. But wait, there's a catch. Real telescopes have all sorts of noise, from atmospheric distortions to sensor limitations. The algorithm's success in simulations is impressive, but translating that into actual data will be a nightmare. Still, this paper isn't just a theoretical exercise. It's a roadmap. Hardware developers now have a target. And if they can build this, we are not just finding planets, we are peering into the possibility of alien ecosystems. So, what's the bigger picture here? This isn't just about quantum physics or exoplanets. It's about how we are redefining the limits of observation. If we can detect planets that are 100 million times fainter, we are not just expanding our cosmic neighborhood, we are challenging the very foundations of how we perceive the universe. And that's the kind of breakthrough that changes everything.